Good day, everyone. My name is Rebecca Lilly with the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Policies for Electrification of the Car Fleet in the Long and Short Run. We are grateful to Dr. Snorre Kverndak for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services that you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over. First, this webinar is being recorded for those that cannot be participated in today's live event. If you have questions, please click the Q&A button at the bottom of the Zoom window and type your question. We have allocated time at the end of the webinar to read and answer them. And now I would like to introduce you to our speaker, Dr. Snorre Kverndak, Senior Research Fellow at the Frisch Center. Snorre, over to you.
Thank you, Rebecca. So I'm going to share my screen. So as Rebecca said, the title of my presentation is Policies for Electrification of the Car Fleet in the Short and Long Run. So most countries have short and long-term goals for the greenhouse gas emissions after the Paris Agreement. So for instance, if you take the European Union, has a goal of reduce emissions by 55% below the 1990 level by 2030. And the goal is to be carbon neutral by 2050. So there are different abatement options to reach these goals, and I'm going to distinguish between what I call static and dynamic options. And the way I define these options are, well, start first with the static option. The static option does not affect the cost of future emission reductions at home. So if you do abatement using the static option, it does not affect the cost of abatement in a later period. Examples could be an obvious example is emission trading. If you buy something from buy emission permits abroad, it doesn't really affect our abatement options or the cost of doing abatement at home. What I'm going to use in my example is subsidies to electric vehicles, because I'm going to show you an example on of electrification of the car fleet. So subsidies to electric vehicles has an impact on abatements, because using fossil fuel cars gives emissions of CO2, but and electric vehicles does not give direct emissions of CO2. On the other hand, we have these dynamic options, which actually affect the costs of meeting emission targets. And examples of that is investments in infrastructure. If we go to the example with electric vehicles, the infrastructure may be chargers or fast chargers for electric vehicles. And these chargers have a much longer lifetime than the cars itself, even if they get depreciated over time. Another thing that matters when you look at the costs of meeting the goals during the 2 time periods, 2030, 2050, is the flexibility. There is flexibility within a time period, say within the first time period, 2020 to 2030, which we call spatial flexibility. One example is emission trade system in the EU, the EU ETS. And the EU ETS covers sectors like power production, industries, and also international aviation within the European Economic Area. The other sectors are non-ETS, and that is mainly transportation, apart from international aviation, as I mentioned. It's also waste burning, it's emissions from buildings and agriculture. These sectors are not part of the EU ETS, but they also have some kind of flexible mechanisms. So it opens for some emission trade within the non-ETS and also some trade between non-ETS and the EU ETS. So there is some flexibility here. We can also define flexibility across time periods, say across the time period up to 2030 and the time period after 2030, which we call intertemporal flexibility. And that is mainly banking and borrowing of emission reductions. And that's allowed to some extent for the non-ETS. So in this presentation, I would try to answer the question, how would the optimal combination of static and dynamic abatement options be under different flexibility rules? And I'm going to use the electrification of cars in Norway as an example. So this is based on a paper I've written, a recent paper actually, I've written together with my colleagues here in Norway, Katrine Hagen, Erik Nevdal, and Knut Einar Rosendal. So to give you some more understanding, I have a few equations here, but just to give you some more understanding of what this is about. So consider that we have emission goals in two periods, as I mentioned already, say period 1 and 2, which may be 2030 and 2050. We have two abatement options. One is dynamic option, which we call E, and one is a static, which is called F. And the abatement cost function for period 1, C1, is a function of different abatement following from static option and dynamic option. And the cost will increase the more we do of both of them. So the more static abatement we do, the cost will be higher. The more dynamic abatement we do, the cost will be higher. Then we look at period 2. So C2 is the cost of abatement in the second period. And again, it depends on the abatement done in the second period. So it increases in static abatement in the second period and dynamic abatement. But the clue is that what we did with a dynamic abatement in the first period, so the investments we did in the first period, will actually lower the costs in the second period. So the more infrastructure investments like charging station there is already, the cost will be lower to reach abatement in the second period. So that's actually the clue with the dynamic abatement option. So based on this simple model, we can actually draw a few conclusions. And the first conclusion is that the cost-effective climate policy implies that the marginal abatement cost of dynamic policies exceed the marginal abatement cost of static policies in period 1. So it may be cost efficient to actually do some more expensive abatement in period 1, which may be investment in infrastructure. And this actually follows from this simple equation we see here. So we know that cost-effective policy actually means that the marginal abatement cost should be equal across the different options. But one thing we know that abatements in the dynamic option in period 1 will actually reduce costs of abatement in period 2. So even if this dynamic abatement marginal cost is higher than the static, it will actually reduce the costs in the future. So in an intertemporal cost function, it may actually be well worth to do some more expensive abatement today because it will actually reduce costs tomorrow or in the next period. So two other conclusions we can draw from a simple model like this. This is actually to try to see how emission trading will affect the two abatement options. Well, that's not so easy even in a simple model like this because it depends on what kind of assumptions we do. And if you use assumption based in our numerical model, as I'm going to show you later on, this is a cross derivative. So meaning that it's negative, that meaning that if you do more abatements in the dynamic option, it will actually reduce the cost of abating in the static option. And this can be intuition with this is actually if, for instance, if you build more charging stations, more people will buy an EV, and we don't really need to we don't really need to have so many subsidies of EVs to do that. So it actually will reduce the costs of the static option. So I'm going to go more into detail with this. But so one conclusion, if you assume that this is the case, and if you assume that we have a permit trading, an increase in the permit price in one period makes it profitable to increase both static and dynamic abatement in the other period. So for instance, if you have if you expect the premium price to be higher in the future, we may actually do abatement both in the static and dynamic option today, increase that. And the reason for that is that because we have some kind of costs of adjustments, like an convex investment function, it will actually be better to smooth out the investment over time, not to take all the investments later on, because it will actually be more expensive if you do all the investments in period 2. It will actually smooth out and increase investments in this period. And increasing investments in this period actually also makes that it will be cheaper to use the static option. We don't really have to, the cost of using the subsidy is not going to be so high. And we also find from this simple model that the impact will be larger for the dynamic option, because that's actually the one thing we want to smooth out. We want to do more investments. I'm going to follow up this later on when I use my example, which is the electrification of the Norwegian car fleet. So if we look at the Norwegian car fleet, Norway is the world leader in the electrification of the car fleet. In 2021, meaning last year, 65% of new cars were electric in Norway. And electric cars counted for something like 16% of the car fleet. So 60% of the car fleet is electric. And why is that? Well, it depends on the policies we have been doing. In Norway, we have high taxes on cars running on gas or diesel. And we have several tax exemptions for electric vehicles. For instance, we have no VAT, no tax on first-time registration of electric vehicles, no import tax. We also have lower prices on driving on toll roads and also on parking in cities. And to some extent, electric vehicles can also drive in the bus lanes. So if this means that we don't really have a direct subsidy on electric vehicles, but these can actually be kind of translated into a subsidy. So if you have all these exemptions, it can be considered a kind of subsidy. And in our calculation, that counts for about 20% of the costs of driving a electric vehicle. Okay, so I'm going to use electrification of the car fleet in Norway as the example. And also in Norway, when it comes to building charging stations, we have no subsidies for building charging stations in urban areas. So most of the electric vehicles are in the urban areas, and so it's profitable for private investors to do investments without subsidies. However, when it comes to rural areas, there are fewer electric vehicles, and the government has a policy that it subsidizes 40% of costs of building a charging station. Okay, so now let's turn to what we're going to do then. So we assume that there's a goal for emissions from transportation in 2030 and 2050, based on the Norwegian goal, and also so Norway is part of the EU climate policy. So the goal is to reduce emissions by about 50% in 2030 compared to 2020, and about 100% in 2050 compared to 2020. So going to be, in my model, I'm actually going to smooth that out, kind of annual emission reductions. So in our model, the government has two options to meet this goal. One is the static option, to have a subsidy to EVs or buy emissions permits using the flexible mechanisms in the non-ETS. We have this dynamic option, which is actually investments in charging station in rural areas, not urban, because that's profitable for private investors to do, but it's investments in charging stations in rural areas. So what is actually the costs of electrifying the car fleet? Well, the social costs can actually be divided into three different terms. One is the cost difference between driving cars running on fossil fuels and EVs. And this is actually cheaper, even without subsidies, because it's much cheaper to run a car on electricity than actually buying gas or diesel, because of the high taxes already on gas and diesel. But there is a disutility of driving an EV. So even if it's cheaper to drive a car on electricity than on gas or diesel, most people still, or a lot of people still don't buy an EV. And the reason is that there is some kind of disutility of driving an EV. And this disutility can be divided into two terms of anciency, range, anciency, which is following from the limited range of batteries. So because of the limited range of batteries, people are actually afraid of not reaching a charging station in time. So this anciency is actually falling in charging stations. So charging station has an impact on this disutility. We also have the charging anciency, which means that we are afraid of long queues in front of charging stations. This also falls in the number of charging stations, but it increases in the number of EVs. So increasing the number of EVs on the road has actually an negative external effect on other EVs because it increases the queues in front of the charging stations. So the benefit of investing in charging station is to reduce these two types of disutility. In addition to that, we have also investments in charging station, and we assume that there is some kind of we have some convex investments costs, so there's kind of adjustment cost in doing that. Or we can think that we invest in the cheapest charging stations options first. Okay, so in this model, let's first define the total utility of all EV owners. The total utility can be divided into 5 different terms. The first is the utility from driving. And then we have minus all the costs. The charging anciency in urban areas, the charging anciency in rural areas, range anciency, and the net costs of driving an EV. We assume that there is a kind of heterogeneity in preferences for driving an EV, meaning that the additional utility from adding a new driver is falling. Additional utility of driving an EV is actually falling because there is some kind of heterogeneity in preferences. When it comes to the total utility of driving an ICEV or a diesel or gas car, we model that in a much simpler way. It's the utility from driving minus the cost of driving. So the only heterogeneity in this model is the heterogeneity among consumers in the preferences for driving an EV. So solving a model like this and try to find the optimal investments and optimal subsidies, we have some simple conclusions so far. We find that optimal investments in charging stations increase in the cost of driving an EV. So the more expensive it is, the more charging stations do we need to build to actually reach the targets or mission targets. But it falls in the more expensive it is to drive an diesel and fossil diesel or gas car. Investments increase in the disutility of driving a car, the charging anciency in the rural areas, and the increase in the range anciency. And it falls in the number of urban charging stations. The more urban charging stations, the more people will actually invest in an EV. We do not need to invest so much in the rural areas because of that to reach a target. The second conclusion here is that the optimal subsidy to EVs actually fall in dynamic abatement. The more charging stations there are, the more people will buy an EV even if the subsidy is not so high. Okay, so in this model, I mentioned in the beginning that I'm going to look at different flexibility also. So I've derived some conclusions from different flexibility scenarios. The first is the case where we do not have an emission cap, and then we introduce emission trade. Then we have no emission trade as next example. We have emission targets in each period without emissions trade, and we have full intertemporal flexibility, banking and borrowing without emissions trade. And then we introduce emissions trade first with spatial flexibility. We have emission trade within each period. And then we have full intertemporal and spatial flexibility. So we can have emission trade, including also banking and borrowing. And we do this exercise for two different prices of permits, a low price and a high price. So this table summarizes some of the conclusions. So it's a lot of information here, and I'm not going to go through all of this. I'm just going to give you some clue what this is about. So in the initial situation, in 2020, we used 7% share of EVs. Today it's much higher, it's actually 16%, as I mentioned to you. And we had a number of charging stations. We have 1,000 charging stations in this starting situation, initial situation. So first looking at the situation for 2030 and 2050, if we do not have any emission targets. So even if we do not have any emissions targets, it's optimal to do a lot of investments in charging stations, which will increase the share of EVs on the road. The reason for that is that given the initial situation, there is a lot of this utility of driving an EV still. So it's actually socially beneficial to do some more investments in charging stations to reduce the social costs. So what about if we introduce emission targets? S1 and S2 are without any permit trading. Without any permit trading, we have actually a goal for each period, 25, 34. The share of EVs should be 35% in 2030 and 77% in 2050. This is a kind of annual target, which we actually smooth out. So the same for every year. So if there is no emission trading, the share of EVs should be the same as the target. And we increase the number of charging stations quite a lot in both periods. So this column here is the share of dynamic abatement compared to total abatement. And all abatement should actually be dynamic in the first year. In the first period, in the second period, it should still be the main abatement should be dynamic. Well, and the reason why it's falling in the second period is that the benefits of building charging stations will fall over time. So it's actually the more charging stations there is, the less is the marginal contribution of building a charging station in terms of reducing this utility. So the benefits of building charging stations will fall in charging stations. If we have a full intertemporal flexibility, no emissions trade, it's optimal to kind of smooth out the abatement over both periods. Still, the main abatement should come from the dynamic options. Then we look at 3 different cases of emissions trading. So if you have spatial flexibility, that means emission trading within each period at what we call the low permit price, €64 in 2030 and 160 in 2050. We should actually have less abatement than if you have no flexibility. So it's actually beneficial to buy permits. But still, if you do that, the most of the abatement should follow from dynamic option. If you have higher price, it turns from buying permits to selling permits, especially in the first period. So the price actually has impacts on if you want to buy or sell, which again has impacts on investments made. So we see that investments is going to be higher for charging stations if the price is higher because we want to do more abatement. The final case here is actually a case where we have just one permit price, meaning that we have intertemporal and spatial flexibility. So the price is equal across periods. In that case, the price is higher in the first period and lower in the second period. So we should do more abatement in the first period and less abatement in the second period. So it smooths out actually. So just summarizing some of the conclusions so far. If you have no emission trading and also no emission cap, It's still optimal with electric vehicles, but no subsidy should be used, only investments in charging stations. So I should mention that this is very dependent, of course, on the assumptions we do. But in our model, this utility of driving an EV is so high, so investment in charging stations is actually the main policy option we should use. If you have emissions caps without flexibility, so if there are no flexibility, then we should have mainly investments in charging stations. If we introduce intertemporal flexibility, we should have more abatement in period 1 than we had without any flexibility, and we should also use subsidies in period 2, period 1. So because the reason for that is that we have diminishing returns from new stations. So if you want to do more abatement, returns from building charging stations falls, and we should also use the static option. If you turn to the cases with emission trading, summarizing what I said in the beginning, if you have a low CO2 price, you should buy permits, mainly the second period, which means that we have a lower investments in charging stations. If you have a higher CO2 prices, we should sell permits in period 1, and we should actually have more abatement, also building more charging stations. In the case with emission trading and spatial and intertemporal flexibility, that is the case where we have just one permit price, which is the weighted average of the high price. Then we should sell permits, and we should high investments in the first period to make abatement in the second period cheaper. So if you have a lot of abatement in the investments in the first period, that will actually reduce the cost of doing abatement in the second period. Okay, so if you remember from the beginning of my presentation, I draw a few conclusions from just the simple cost functions. And one of the conclusions I showed you in the beginning, which I promised to return to, was that if you have a spatial flexibility, that means we have emission trading within each period, so within 2020, 2030, and within 2030, 2050. Then if you have an increase in the permit price in one period, that makes it profitable to increase both static and dynamic abatement in the other period. So let's start with period 1 then. So if you have permit price in period 1 along this x-axis, you have abatement measured in million tons of CO2 along this vertical axis. We see that an increase in the permit price in period 1 actually increases both abatement options in period 2. So this is the dotted lines. So this is static option, which increases in period 2, and the dynamic option, which increases in period 2. It's not so visible from this graph, but one of the conclusions in the beginning was that the dynamic options should increase more than static. And if you look at the number, this is actually the case. So, let's look at period 1 then. If you have a higher emission price in period 1, we want to do more abatement at home. And as the benefits from investing in charging station, we will invest more in charging station in period 1. As the benefits fall, the higher the investments are, the more profitable will it be to use the static option. So in period 1, we'll actually increase the static option more than dynamic option. Okay. So what about the case where we have an increase in the permit price in period 2? So that is that we expect the permit price to be high in the future. So what do we do then? Well, what we do in period 1 is that we increase investments in charging stations in the infrastructure, because we want to smooth out. It will be quite costly if we want to do all the investments in period 2. So we want to increase investments in the infrastructure in period 1, and dynamic option, the infrastructure abatement, is going to be increased more than the static option when the permit price increases. So this is the conclusion we had before. And again, in the future, when we have done the investments in period 1 and we want to reduce more, it will be optimal to increase the static option to meet that, because the diminishing returns of charging stations. We have a quite high level of charging stations is going to be higher, the higher the permit price is. But we have diminishing returns of charging stations because so this utility doesn't fall so much if the stock of investments or the capital is already very high. So then it's optimal to use the static option, which is actually to subsidize EVs. Good. So then I turn to the case with intertemporal flexibility. And that means everything is flexible. We have permit trading and we also allow banking and borrowing. In that case, when everything is flexible, there's only one price. One price in period 1 should be equal in present value to the price in period 2. So if the one price increases, we also see that the sales, the demand for permits actually decreases and we start selling permits. This means that abatement has to increase, and when dynamic options increase over time, that means that the benefits from these investments in terms of reducing this utility falls, and then it's optimal to use the static option. So far we have seen that the dynamic option is the optimal choice in our model, and static option is only worthwhile doing only if the benefits of reducing this utility is very small. So, but this result is of course very dependent on what we assume about this utility of driving an EV. And it's quite hard actually to find some good numbers when we want to calibrate a model like this when it comes to this utility. So one thing we know is that if we assume that this utility is very small, then the investment should also be smaller in charging stations. If this utility is very high, investment should be higher. So the point with investments in charging stations is actually to reduce this utility of driving an EV. Okay, then I sum up my presentation. So with cost-effective climate policy, the marginal abatement cost of dynamic option alternative exceeds the cost of static abatement, such as, for instance, the permit price. And this paper is not the first one to point to this, but this is actually a kind of starting point that follows from the model also. It's worthwhile to do some kind of expensive abatement options in the beginning, because that will actually reduce the costs of meeting targets in the future. So one main thing is that the flexibility has impacts on the choice of abatement options. So I'm showing different results when it comes to investments in charging station, depending on flexibility. One example could be when we have a permit trading. A higher expected price in later periods can make it more profitable to use the dynamic policy instrument, which meaning investment in charging stations today, while the opposite may be a result for a higher permit price today. So what we expect of a permit price, for instance, how the system functions out when it comes to flexibility, has quite high impacts on the investments we should do today. So one conclusion to draw from this also is that as options have a large impact on policy choice, investment decisions, this stresses the importance for early and consistent plans for regulations of international emissions. So if the government and private investors are going to do time-consistent investments, you should also have time-consistent plans for regulations of international emissions. Okay, so let me now turn to, if I stop sharing, let me now turn to the Q&As. Right. Well, I don't see any questions so far. Okay, so maybe I should turn it over to Rebecca.
Great. IAEE would like to thank Dr. Snork Forndok for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.